Let's try using the method of trig substitution to evaluate this integral, the integral of 1 over x squared minus 1 dx. Now, according to our guidelines for trig substitutions, for expressions of the form x squared minus 1, like this one, we want to use the substitution x equals secant of theta. And we use a substitution because we're going to take advantage of the Pythagorean identity. Secant squared of theta minus 1 equals tangent squared of theta. So let's try actually making the substitution and see what happens. So I'm going to let x equal secant of theta. I also need to find an expression for dx. So the derivative of secant theta is secant theta tangent of theta, and then I'm going to have a d theta. So then if I rewrite my original integral using this substitution, I get 1 over secant squared of theta minus 1 in my denominator, and then my dx is replaced by secant of theta, tangent of theta, d theta. Now in my denominator, I'm going to use this Pythagorean identity to rewrite secant squared of theta minus 1 as tangent squared of theta. So I have 1 over tangent squared of theta, and then times secant theta, tangent theta, d theta. So I see now that I can reduce this a little bit by canceling out a factor of tangent of theta from the top and the bottom. So if I do that, it's going to leave me with the integral of secant theta over tangent of theta d theta. So now I have this integral involving trig functions, and we've learned about these types of integrals in the past. There are likely several ways that we could approach this, but what I'm going to try to do is try to rewrite both the secant and the tangent in terms of sines and cosines, and see if by doing that I can simplify things any. So hopefully you remember that secant of theta is 1 over cosine of theta, and that tangent of theta is sine of theta over cosine of theta. So then if we rewrite this integral using those facts, this secant is in the numerator, right? So I'm just going to have 1 over cosine of theta from that. But my tangent is in the denominator, right? So it's 1 over tangent. So then this is going to be times cosine of theta over sine of theta. So when I do this, I see I have a factor of cosines that I can cancel, and I end up with the integral of 1 over sine of theta d theta, which is the cosecant of theta. Now we just recently learned the formula for the antiderivative of cosecant of theta. Right? We learned how to derive that using methods for trig integration. And that antiderivative is the negative natural log of the absolute value of cosecant of theta plus cotangent of theta plus c. So we have an answer now, but the final step for these trig substitution problems is to, in the end, write this in terms of our original variable. So I want things to be in terms of x instead of in terms of theta. And typically what that involves is using a right triangle to figure out these different trig relationships. So let's review how that works. So what I know is my original substitution, that x equals secant of theta. But I don't know what cosecant of theta or cotangent of theta equal. So then what I'm going to do is I'm going to use this relationship x equals secant of theta to set up a right triangle. So one way we can think about this is that secant of theta equals x over 1. So secant of theta is the reciprocal of the cosine, and the cosine is adjacent over hypotenuse, right? So this should be hypotenuse over adjacent. So the hypotenuse of my triangle is x, and the adjacent side with respect to theta is 1. Now, to figure out the cosecant of theta and the cotangent of theta, I'm going to need to know this other side of my triangle. And I can find that using the Pythagorean theorem. So I will just, for now, call this side B. We can set up the relationship that 1 squared plus b squared equals x squared. So if I solve for b, I get that b equals plus or minus the square root of x squared minus 1. Now remember that we said earlier in the lesson a very important fact. When we make our trig substitutions, for example, here we did x equals secant of theta, there were restrictions on theta, and that just comes from the range restrictions on the inverse trig functions. But we said that these restrictions have an important consequence for us, and that consequence is that we will always be able to use the positive root when solving for the sides of our right triangles. So then I am going to be able to just use this positive root here, which means that my unknown side here it has a length of the square root of x squared minus 1. So now based on this triangle, I should be able to write down what the cosecant of theta is and the cotangent of theta are. Now the cosecant is the reciprocal of the sine. So the sine is the opposite over hypotenuse, so cosecant should be hypotenuse over opposite side. So that should give me x over the square root of x squared minus 1. And then cotangent of theta is the inverse of the tangent. Tangent is opposite over adjacent, so this should be adjacent over opposite. So that looks like it should be 1 over the square root of x squared minus 1. So once I know these, I can go back to my antiderivative here that I had found in terms of theta, and now I can write it in terms of x. So this looks like it should be negative natural log of x over the square root of x squared minus 1 plus 1 over the square root of x squared minus 1 plus c. So negative natural log of x plus 1 over the square root of x squared minus 1 plus c. And perhaps I could make some more simplifications there, but we will stop here and take this as our final answer for this original integral, 1 over x squared minus 1 dx.